Now we're ready to talk about series solutions to ODEs. Sorry, I had the outline up from when I put it on the screen. So we're going to begin with a quick introduction. It's going to be our last little bit of vocabulary so that we can kind of like state the type of problem where we can apply this approach. And then we'll go through the steps we use and some examples implementing those steps. So we're going to be talking about series solutions to the differential equation given by y double prime plus p of x y prime plus q of x y equal to 0. And I'm just going to note that the point x0, for us, that's going to be 0 usually, is what's called an ordinary point. If p of x0, q of x0, let's put this on top. If those functions are analytic, so that means we can't divide by 0, have negative roots, etc. And then if x0 is an ordinary point, then y equal to the infinite sum n equals 0 to infinity c sub n times x minus x0 to the power n is a solution to the ODE. And that solution will have some radius of convergence, and some coefficients c sub n. And then if we want to actually know what that solution is, we need to solve for c sub n such that the ODE is satisfied. So this is kind of our condition to be able to solve this type of problem. We need to be looking at a problem like this. We need to, for x0, which is 0 for us in most cases, make sure that p of x0, q of x0 are well behaved. Then we know that we can plug in y this way, manipulate everything to solve for Cn, and we will have a solution y to the differential equation. So we're going to go ahead and outline the actual steps we follow to make that happen. And I'm going to go ahead and put that on the next slide. That way hopefully it's all in one place for you. So pause if you're still writing. So these are going to be our steps we follow, and we're assuming that x0 is 0. So first thing you need to do is make sure the ODE is in the correct form, where you have y double prime with nothing in front of it, plus p times y prime, plus q times y equal to 0. Reason is because we have to check that p and q function, and so you need to make sure to divide by whatever's on y to have the correct, y double prime to have the correct p and q. So then once you've done that, you're just going to check that p of 0 and q of 0 are well defined. So kind of like when we did those initial value problem theorems for existence and uniqueness, it's going to be okay if there are other points where they're not well defined. Like, so suppose you have like an x minus 4 in the denominator, so 4 is a bad value. Those are okay. It just affects the radius of convergence where your solution is guaranteed. It doesn't change whether or not we can do this process. So any other points that break P and Q affect radius of convergence. But you don't need to worry about it for setting up the problem. So then once you know that this is an acceptable approach to take, you're going to assume a solution. We're going to take this series solution from n equals 0 to infinity of c sub n x to the power n. That's our x minus a that we've been seeing, but our a is 0, so it's just x to n. And most recently, we spent so much time with Laplace. It's been a while since we assumed a solution and plugged it in, but that's what we're going to do. We're going to take our derivatives. And I know we wrote them in the last video, but I'm going to put them here so they're next to your steps in the notes. Y prime is 1 to infinity of n Cn x to n minus 1. And y prime is sum from 2 to infinity n times n minus 1 Cn x to n minus 2. I don't want you to memorize that. I think that you should be able to figure out why those are the derivatives, but I know that series are really intimidating, so you know, it's fine if you just want to take those things and plug them in. You're working with enough complicated things as it is. So, after you've taken those derivatives, we're going to plug y and its derivatives into the ODE. Remember, we just want to solve for whatever has to be true for them to be solutions. But because series are pretty complicated, it's going to be a complicated few steps to get there. So what we need to do is we need to manipulate into a single series. And then I'm listing in the order that you will do this. You need to make sure that they have the same power. First. And then you're going to make sure that they have the same lower bound, n equal to k. Usually that's going to be n equal 1 or n equal 2. So fix it so that the powers match, then fix it so the lower bounds match. Really do it in this order so you don't have to like backtrack and undo steps on yourself. Once you have it in a single series, you're going to solve for relationships using your coefficient c sub n. That make the single series equal to 0. Because the right-hand side of the equation is equal to 0. So in particular, you're going to take everything that's multiplying your x to n in that series, and you're going to set it equal to 0. That's that like condition for something to be 0 valued that we talked about in the introduction to series video. And then finally, you should have two unknown coefficients that are kind of like left over after you solve for those Cn. And You're going to solve those using initial conditions in an initial value problem. If you're not solving an initial value problem, you'll just leave those unknowns C0, C1 in your general solution. And those are the steps to solve this type of differential equation using series. So in the next video, we'll go ahead and start setting up our first example of this.